I'll begin with a word of prayer. Heavenly Father, we thank you again for this opportunity we just have to meet and study your creation together. I pray for this class that you be glorified in what we do. And it's just again to pray to encourage the students just to do their best each day, Lord, for your glory. In your name I pray, Lord Jesus. Amen. Okay, so we're beginning Green's theorem now. And so this is section 7.5 in my notes. And I need to introduce a new concept, which, well, it's simple enough. So here's the idea. We can talk about flux in two dimensions. So here's basically the idea is this. If I've got, say, a curve C, all right, then I can calculate the flux of a vector field through it, all right? And so let me show you like two cases. One would be like this. All right, suppose the vector field's like this. So then the flux would equal, let's say that this vector field's F. So the flux would be something like the magnitude of F times the length of the curve C. All right. On the other hand, if your curve C looked like this and your vector field, looked more like this, right? Then the flux, in this case, is equal to 0. So another way to say this is the flux through a given curve, it's counting the number of field lines that go through. It's counting the number of integral curves to the vector field which go through. And they're only really counting in as much as they are cutting through the curve, all right? So we're getting flux from a vector field. So here's another example. If I had something like this, I could have a closed curve. Here's another closed curve, right? And maybe I've got some place where all my my streamlines are coming out of it like this, all right? And over here, here's another one. My streamlines are coming out of it like this. Whatever. And in this one, I'm supposing that the streamlines are pointed this way. So you guys remember what this picture means? This picture means that the vector field aligns with the curves, right? So these curves are like tangent vectors. The tangent vector fields to these curves that I've drawn in red, they would align with the given vector field, all right, which I have not. So there's two different ways to picture vector fields. The one is just by drawing an array of vectors, right, like this. The other way is to draw streamlines, or field lines as they're sometimes called, like that, all right? So in this case, what would the flux be? Well, the flux, so if we're using the convention that the number, like we draw one field line, the more field lines we draw per unit area, let's say, the more strong the magnitude of the field, all right? So in that system, the more field lines you have cutting through a curve, the greater the flux. So to calculate flux in whatever system of units I'm talking about here, you can just count the number of field lines. So like here, the flux would be 1, 2, 3, 4, 5, 6, 7. So the flux here would be equal to 7. And over here, the flux would be what? Assuming that I'm using the same, system here. 1, 2, 3, 4, 5, 6, 7, 8. But in this case, they're all going into the interior of the curve, all right? So the convention is to say that's minus. That's a negative flux. Now, so really, this doesn't quite capture the idea, because really when we talk about flux, we're talking about a closed curve, all right? And so, and we're counting field lines that go out as giving you positive flux, whereas field lines that go in as giving you negative flux. All right? Is the idea clear enough? So, definition, for F continuous on open set containing closed curve C, and I should be a little bit more simple. What is a simple closed curve? I'm not sure I really need the simple there, but well, let's just leave it there. Then the flux through this curve, the simple means that it doesn't have, like a figure 8 wouldn't be a simple curve, I don't believe. I don't think you could have self-intersections, for example. So a simple curve, I believe, would it would enclose a simply connected region, which is a region where you can deform loops to a point without getting hung up on points outside the space. Anyway, the flux through the curve would be equal to the integral with respect to arc length, all right, of the dot product of the vector field with n, I probably should put an n hat there, ds. Now here, this is not the normal we've talked about before, okay? So this n hat, let me picture on my hypothetical curves above, okay? N hat would look like this. So could you put this into words? What is n hat? It's the normal, but what kind of normal is it? It's a unit normal? That's true, because I put a hat on it, right? You got me there. My question, how about this? Is it the Frenet normal? Is it the big N we talked about before? Search your heart. Search your feelings. Sorry, I'm an idiot. What? This is in 2 dimensions, yeah.
So it can't be the Frenet
So it's your argument's by dimensionality, but we could calculate the Frenet frame and limit it to 2 dimensions. Like there's nothing stopping us from calculating the Frenet frame for a planar curve. Like we've done that. Most of my test questions are in planar curves, right? Because that gives me an easy torsion question, 0. This is not the Frenet normal, because the Frenet normal points towards the center of the osculating circle, right? So the Frenet normal is actually opposite. Well, it depends, doesn't it? It is the Frenet normal here, right? Because the osculating circle to the curve's out here. But here, the osculating circle's inside the curve, right? So sometimes it's the Frenet normal, sometimes it's not. This is a different normal. This is the outward pointing normal. Outward pointing normal to C, all right? And so it would be nice to have a, a formula for this, and there is one. I'll just point this out. If the unit tangent is equal to, let's say, dx ds, dy ds, so suppose we've parameterized with respect to arc length, okay? Then that tells me that my unit normal is equal to dy ds, comma, minus dx ds. Now, can you see that? Like, look at the pictures up there and convince yourself that that's the legitimate formula for the outward pointing normal. let me just draw a couple of unit normals, and let's just check this formula. All right, let's just check this formula. So like here, let's see here. So we have to give the curve the positive orientation. I should mention that we're orienting it in the counterclockwise fashion. So like this, right? So there would be my unit tangent. And over here, for example, would be my unit tangent. All right? So let's see here. That unit tangent has, it's what? It's pointing right and up. So dx dt and dy dt are what? They're both positive. How about the unit normal? So these are both, the derivatives are both positive, which means we're going to the right and down, which is exactly what happens here, to the right and down. How about this one up here? Here we've got dx ds negative, and we've got dy ds positive, right? Because it's pointing into the second quadrant. That is the tangent is. Oh, my bad. Where's the, I got to keep track of my arrows. I'm looking at the green arrow. Where's t pointing? Into the third quadrant, right? Both components are negative. So dy ds and dx ds, they're both negative, which means this is negative. Minus a minus is a plus. So it's going to the left and up. To the left and up, right? You can check every single case. That gives you the right direction for the outward pointing normal. Provided what? Provided we're talking about a counterclockwise oriented curve, right? So that's our convention.
So that's probably why you can't use a non-simple curve.
Yeah.
On the inside.
Yeah, so we'll just keep it simple, right? So there's a formula here. And the formula we can calculate. Flux of the curve C is the integral, this circle is like decoration. It basically is just emphasizing it's the integral around a closed curve. That's all that means, okay? And you can adorn it with an arrow. You can adorn this with the appropriate arrow to indicate that it's a clockwise one, like so, counterclockwise rather, so like this. If you do that, then you're saying closed curve counterclockwise. That's all wrapped up in that symbol, which is kind of nice. But anyway, so suppose we're looking at f dot n hat ds. How can we write that? Well, look, that's the integral of, let's say, pq dotted with n hat. Well, n hat we just learned was dy ds comma minus dx ds, right? ds. So what are we looking at here? We're looking at p dy ds minus q dx ds, right? Which is equivalent, I mean, it's not equivalent, it's the same. This is just another formula for the integral of p dy minus q dx. So that is a very nice formula because now, look, isn't that nice? Now we don't have to care about the outward pointing normal. We can just calculate the integral of that vector field. Does that make sense? So that's pretty nice because we already know how to calculate those kind of integrals, right? So example 1, we could do something, pretty simple, like let us calculate, let's let f equal to, I don't know, x comma y, and we'll let our curve be the unit circle. So that means that, x is equal to cos t, y is equal to sine t. So dx is minus sine t dt, and dy is cosine t dt. So if I'm going to calculate the flux of this vector field through the unit curve, right, unit circle, well, I got to integrate, let's see here. My p is x, so I've got x dy minus y dx, right? That's what I'm integrating here, but now just plug in the formulas, right? What are the formulas here? Integral from 0 to 2 pi. My x is cos t. My dy is cos t dt. Man, these integrals are so boring. It's always the same thing, isn't it? So you got sine t minus sine t dt. So we got what? Cosine squared plus sine squared, also known as 1, right? You know, I'm not simplifying sine squared plus cosine squared as 1 in this integral. That exacts a heavy price from you, doesn't it? So anyway, there you go. The flux of this vector field through the unit circle is 2 pi. Does this make sense? I mean, it's calculation, but any questions? Do, 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 do. Okay, so I want to show you something that's pretty neat. We're going to look at a way to approximate the flux by direct computation. We're going to look at a triangle, all right? A triangle? What's wrong with me? Good night. Does that look like a triangle to you? Good night, I tell you. Dummy. All right, x comma y. Over here, I've got x plus delta x comma y. So I'm just labeling the corners, okay? So we're going to base the rectangle at xy, and then we're going delta x over and delta y up, okay? So here you got x plus delta x, y plus delta y, and this guy up here, of course, would be x comma y plus delta y, all right? And I'm trying to figure out what is the flux of the vector field PQ. All right, what's the flux of the vector field PQ through this rectangle? So I'm trying to find flux of F equal to PQ through the boundary of the rectangle. Is there something unclear? Is this what? Exactly. Oh no, this is a derivation. So the flux depends on the unit normal, right? What's the unit normal to the rectangle's sides? It's different in different ones, right? So like here, n hat, here's n hat, here is n hat, right? And down here is n hat. So you tell me, I'll start us out. That's x hat. And this one is y hat. How about this one? Negative y hat. And over here, minus x hat, right? Which component of the vector field gives you flux? Think about it. Well, I mean, so basically you just take n hat. Well, the definition, n hat dot f, right? N hat dot f just picks up what? The normal component. Yeah, so here we get, what's the length here? Delta x. So we get delta x times q for the flux here, right? This one we get delta y. Let me write the vector field first. We get p delta y here, right? This one we get what? We get minus p delta y here for this flux, and down here we're going to have minus q delta x. All right. And then if you just added those up, you'd think you got 0, right? Because why? I haven't done what? I haven't yet appreciated the point dependence, right? So to be more explicit, from the top, we have a flux of like q of, you know, let me be careful to make sure I don't mess up my setup here. Yeah, x comma y plus delta y. Delta x, that's my flux from the top, from the base. I have q of x comma y times delta x. From the right, I've got, you know, p of x plus delta x comma y delta y. And from the left, I've got minus p of xy delta y. Now, of course, you could fuss like, well, anyway, this is just a. Why did I choose the, you know, why did I choose the right or the left endpoint, right? If you don't like this, you could choose the middle points. You could choose the middle points to calculate the flux. Eventually, we're going to take the limit as delta x and delta y goes to 0 to try to see something. So, admittedly, probably logically speaking, it would be a little bit more level-headed. I don't know what you want to say. More careful to use the midpoints to calculate the magnitude of the vector field for the line segment, right? Because the midpoint is shared as the delta x and delta y goes to 0, I suppose. Something like that. But anyway, it's not quite true. There you go. This is an approximation anyway, because of course, if the f is variable, right? This is just an approximation for the flux, right? Because the magnitude varies as you go across these line segments for finite deltas. Yeah? So what's the net flux through the curve here? So the net flux is equal to, well, let me factor out the delta x's, okay? So you got like, you know, q of x comma y plus delta y minus q of xy. And there's a common delta x I can factor out there, right? And then plus you've got p of x plus delta x comma y minus p of xy. And there was a common delta y there, right? You guys with me? What happens if we divide that expression by delta x, delta y? What does it give you? You're like a mess of weird formula, like a messy, weird formula, I guess, but something like that. Yeah, well, fair enough. Yeah, so, and I could say that, yeah, so if I take phi over delta x, delta y, I've got q of x comma y plus delta y minus q of xy over delta y plus what? P of x plus delta x comma y minus p of x comma y over delta x. All right. And so what happens in the limit as your delta x and delta y both go to 0? This becomes what? Do you see what you're doing? You're holding x fixed, you're varying y. This is the partial derivative of q with respect to y. And over here, you're holding y fixed, and you're varying x. So this is partial p partial x, right? And this is the two-dimensional divergence, del dot p comma q. Of course, this is a definition, which perhaps I haven't made yet, unless you wanted just to say that, well, I told you about three-dimensional divergence, right? So this is the two-dimensional divergence, which apparently calculates something about the flux per unit area of a little rectangle. So this motivates the following integral. This suggests that the integral of, partial p partial x plus partial q partial y dA over the rectangle is equal to the integral over the boundary of the rectangle of the flux. Well, what's the flux? We just worked over there that the flux is p dy minus q dx. That is the divergence form of Green's theorem. There's a chair there, apparently. Now, I've just derived it for a little rectangle, right? What if your region's not a little rectangle? How does this argument kind of like, how does this argument scale, let's say? Suppose your region looks like this, right? It's not a rectangle. Can I still say Green's theorem holds on that? Think about this. You can take it and you can approximate it. Well, not approximate it, but you can put little rectangles in here, right? Now let me make some bigger ones over here, just so you can see what's going on better. Now, if each one of these rectangles is counterclockwise oriented, what happens as you think about the boundary? Can you guys tell me how does the boundary of these different rectangles interface with one another? They go opposite directions when they're in contact with each other, provided that they're in contact with each other, right? Think about this. Every interior boundary, so like counterclockwise, right? So this one, it's going like that, right? This one is also going like that. This one's also going like that. But you notice what happens here. Where the right one meets the edge of the left one, the left are going up, but the right are going down. And if they share that common boundary, when you add up the line integral along such curves and their reversals, those add to 0. See that? Do you see that? Then that happens the same for like up here. If this is, again, counterclockwise oriented. So the one on the bottom is going to the right, but the up here, it's going, oh man. What happened? Just a second. Did I just make something? Did I make something clockwise? Just a second. Let me try this again. I have trouble sometimes. So yeah. So this is counterclockwise, right? And this is counterclockwise. I had a clockwise arrow was what my problem was. I tricked myself into drawing clockwise arrows if I'm not careful. The point is, if you actually draw it properly, then you can see that the bottom one, the top of the bottom rectangle is oriented to the left, but the bottom of the upper rectangle is oriented to the right. Where they meet, the shared boundary is a reversal from one rectangle to the next to the one that's adjacent. So what happens here then is if we take the sum, right, over all the rectangles, and let's say the k, well, let's just say k where k is a rectangle. So I'm talking about integral. So we have integral, double integral over the kth rectangle of, let me use the short notation, divergence of the vector field dA. Well, that by applying, applying the Green's theorem for the rectangle to each one, we have the sum over k of what? The integral over the boundary of the kth rectangle of f dot, not f dot dr, but my bad, f dot n hat, right, ds. But what happens, of course, is that this one, in the limit as k goes to infinity, right? In the limit k goes to infinity, we just have the integral over the region of the divergence of the vector field, right? Because if we take the integral of the integral of a union of rectangles is the sum of the integrals. So we can just combine it in the integral of the union rather than the sum of the integrals. And on the other hand, this is more tricky, but as you take the union of all the boundary curves, all of the interior curves are reversals of one another wherever they're covering the same set of points. So this just gives you the integral of the boundary of R in the limit. And I prefer this formula, P dy minus Q dx. All right? So if you can prove it for a rectangle, and you can observe that when you divide your shape up into a union of rectangles, well, the interior edges cancel out. As we take the limit of the number of rectangles going to infinity, we obtain the theorem. Now, admittedly, there's some pretty sketchy analysis right there. How do you take the limit of the number of rectangles going to infinity, right? So to really put that into practice, we'd need a more nuanced theory of integration than we have here. But if you did, this would make sense, all right? So how would we prove this with the technology that is more suitable for this course, right? Like, what do we know about? We know fundamental theorem of calculus. I think this is a legitimate argument, don't get me wrong. Like, I like this argument, it's fine. But it would be good to give you a different argument which didn't rest on, parsing the shape into infinitely many rectangles, yeah. So the other argument basically is just to confront this directly for a simultaneously type 1, type 2 region, all right? So I'll show you that proof in just a second. Now once you know this, right, once you know this, and I think at this point we know it because we went through at least one of the proofs, can you tell me how would you integrate the line integral? Like if you have this form of the Green's theorem, you can do a substitution to get the other one. Let's see that. All right, so let's try this out. I've got integral of p dx plus q dy, right? Over the boundary of some region. So we can write, I want to rewrite that as in the form of the divergence form, right? So let's see here. This is really the same as what? The integral over the boundary of the region of what? Let's say q bar dy minus p bar dx, right? If that was the pattern, we know what to do with the bars over it, right? If I've got p bar dy minus q bar dx, we know that we can apply the divergence form of Green's theorem and get that this is equal to the double integral over this. And here, by the way, this r, we're talking about what? R looks like this, right? It's a simple, it's a region simply connected. It's got no holes in it at the moment, right? We'll punch some holes in it in a later lecture, just not yet. You can do it. It just requires more discussion. But for now, no holes. So if we believe what we just did over there, we know that this is equal to partial p bar, partial x, plus partial q bar, partial y, integrated over the area, right? So how can you guys tell me, what substitution do we need to make right here to make this go? What do I need to, what's my definition for Q bar and P bar to make this so? I need what? So I'm just making sure I have the letters in the right order. dy. Yeah. Looks like we need Q equal to Q bar, right? Is that right? That feels wrong, guys. Yeah, that's what it would seem to say, wouldn't it? Well, P bar equals to minus P, right? Well, that's what logic told us. So let me just assume I haven't made a mistake for a second here. Something's wrong in my mind, but hopefully it's just my mind. No, well, dang it. All right, I've done something. See, I should be getting partial Q partial X minus partial P partial Y over here. But I don't feel like I'm getting that, am I? I'm not getting that. Look at my notes. There's an error in something I'm doing and I don't see it yet. Man, this is annoying. P dy Q dx. Oh, this is it's supposed to be, I'm a dummy. Look, I'm supposed to do what? P bar, good grief. P bar dy, Q bar dx, right? That's what we have to have here. P dy minus Q dx. That's the pattern, I have to do that. Goodness gracious. So if that, because otherwise I don't, that's the pattern, right? That is that, not what I had before, right? I'm just putting bars on what I have on the right board, that's all. If I put bars here, junk, 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 I have that. Before I had the P and the Q flipped over here, which was confusing me a lot. I didn't have them flipped over here, I had them flipped just over there. All right, now that we have that, now tell me, what is the relation? What is P bar equal to? P bar is equal to Q. And Q bar apparently is equal to minus P, right? This is not rocket surgery or anything. It's just this has to match that. That has to match that. All right? But then, what do we got? P bar is Q, so we've got partial Q, partial x minus partial p partial y dA. And so this over here, if we have the integral over the boundary of the rectangle of p dx plus q dy, well, that's equal to the integral over, well, it doesn't have to be a rectangle, it's simple closed region of partial q partial x minus partial p partial y dA. And that is the usual form of Green's theorem. I think you can pretty easily see why the usual form of Green's theorem is like to be preferred, because to use the other one on line integral requires you to make the appropriate identifications of minus and such, which is why you won't even find the divergence form of Green's theorem in a lot of books. But I think it's really worth our time and effort to define the two-dimensional flux, partly as a lead-in to the discussion of surface integrals, where we calculate the flux of a three-dimensional vector field through a surface. That's one thing. But the other thing is that this bootstrapping argument that I had over there in terms of breaking the area up into a bunch of little rectangles and adding up, that actually is a good way to prove all of the major theorems in this course. If we can understand something for a rectangle, we can kind of extrapolate from there. Let me show you guys something. I can. Sorry I got confused about the sign thing. I do that and try not to do it, obviously, but these things happen. There is a corresponding picture for a little rectangle. So, you know, the little rectangle I drew over there and I covered up now. I was calculating the flux of the vector field through the little rectangle. There's a corresponding picture you could make for the curl. Well, not for the curl, rather, for the circulation, right? So the circulation, it counts how we're, you know, lining up the vector field with the boundary, with the curve that we're integrating over. And so, if I can find my way back to, oh man, I have closed my notes. Now I have to find them again. It's annoying. I'll find it. Show yourself. All right, there it is. All right, come on. Whoa, goodness gracious. So, because all right. So here is the picture for curl, right? So I'm calculating how the PQ vector lines up with the little rectangle. So this one would give me like Q delta Y, because the Q points, you know, the tangent direction, tangent vector to the curve is upwards, right? So that picks up the Q delta Y. The distance is delta Y. Then minus P delta X, because, you know, minus X hat dot the vector field gives you minus P X hat, and minus Y hat dot the vector field gives you minus Q, and then delta Y is the length, and likewise down here P delta X. And so that would be the circulation over the little rectangle, all right? And so if we add up the circulation along the top, the base, the left, to the right, you get the work done by the vector field over the little rectangle. The work done by the little rectangle, if we divide by delta x, delta y, we get the difference quotients. But this time, because of the way the things align, we end up with a minus, right? So we end up in the limit that the, and this is a typo. That's supposed to be a w, all right? It's supposed to be a w. Partial q, partial x, minus partial p, partial y. That's the work done by that little, in that little rectangle. which you might recognize as the z component of the curl of PQR, right? Or PQ0 if you like. And so that gives us the so-called curl form, or the usual form of Green's theorem, which is this, right? Now, that said, probably I should show you, we should spend some time on the proof of the theorem next time, so I won't go over it right now. Instead, I will spend the last minute of class showing you an example or two, just to give you a flavor. So suppose we wanted to calculate the line integral of x cubed dx plus yx dy over a rectangle. What would that require in terms of direct computation? Think about this. If you wanted to calculate the line integral, right, of x cubed dx minus yx dy, think about this. What would that mean? This is the unit square, right? How many sides does that have? 4, right? You'd have to break this up into 4 line integrals around the edge. The horizontal bottom leg, the vertical right leg, the horizontal top side, and the vertical left side, right? 4 different line integrals. Yeah? Or you can use Green's theorem. You've got p here, you got q here, so partial q partial x minus partial p partial y. Well, p's got no y dependence, and partial q partial x is just y. So we just do the double integral over the rectangle, and we get a half. Yeah, right? I mean, like, that is incredible how much computation that saves you. Green's theorem is a very important theorem to know about. Because if I say calculate a line integral around a closed curve, it may be that Green's theorem makes it way, way easier. But anyway, that's just the first example of many. We'll do probably Monday and Tuesday, probably still be on Green's theorem in all likelihood. So, what's up?